So the point was that we're going to be careful when we read a book or a paper and make sure that we can also prove from the beginning. And also, so points for proofs. So points for proofs. You know, when I got to grad school and I took this advanced linear algebra class, it was basically seemed like the expectation was that I knew how to do proofs. And I don't know how anyone learned how to do those before they were in grad school. I don't know how that expectation, maybe, but it was also in a different department, so it could be true that in other departments they taught proofs more rigorously. So here's points for proofs. 1, check that you have every condition needed. To go one step to the other. So to go step to step. Never skip a step. Even if you feel like it's intuitive, you have to prove it. Cannot just go. Sometimes intuitiveness doesn't actually hold. And then the last thing was always verify you can do the proofs. And the things you're citing. Because everyone makes mistakes. There might be small mistakes, or even larger ones. If there's larger ones, probably then the person is a little in trouble. But there might be small ones. All things. So what we're going to do now is we're going to talk about, okay, given that this is true, now we're going to go through in a more rigorous way of what's going on with perturbations and how, so this is what's really going on with the perturbations. So we have the x dot equals ax. So what the book says about this is that it says we can get insight into the behavior of a linear system under perturbations by examining the special case of linear perturbations. So let me break down this sentence. What did they just say they're going to do and what they're not going to do? I'm going to take some time on this because I think this is good for thinking about proofs. So they said they can gain insight into the behavior of a linear system, like this, under perturbations. So everything has some disturbances in life. No model is actually perfect. So they're going to ask, but then, okay, this is also a good point. We have an imperfect way of modeling disturbances in control. So they're going to talk about specific kinds of disturbances right now. And it says they're going to talk about linear perturbations. So they're going to say that my model is not fully correct, but it's not fully correct in a linear way. So they're going to analyze a very specific type of lack of correctness. So they said, suppose A has distinct eigenvalues. So they say A has distinct eigenvalues. That means they're different. Distinct eigenvalues. Two different eigenvalues. And that should prevent that case with the 1 on the upper right corner. Yeah. Suppose A has distinct eigenvalues, and so we're going to consider A plus delta A. So the question is kind of now along the lines of, pretend that the matrix is x dot equals A plus delta A x. And how does the fact that this matrix A is different in this very prescribed manner from this A affect the solutions? So you can see this actually has nothing to do with nonlinear terms. Like, this is actually a very, very specific type of proof, which is why I was wrong the other day in what I said. Then, so it says, say that delta A is a 2 by 2 matrix, and the elements have arbitrarily small magnitudes. I'm going to not worry if we go a little slower than my original schedule, because we can do this for the next 5 years. So. So I think it's more important to teach some of these concepts that are hard. So apparently, so then this is also a good point about proofs. So what the next part of the proof says is, from the perturbation theory of matrices. We know, so I'm copying this from the book, that the eigenvalues of a matrix depend continuously on its parameters. So, first, let's break down this statement. From the perturbation theory of matrices, it says we know the following. So, relating this to the steps in proofs, if we were really going to use this in a proof, I would say it's probably a good idea to look up what's the perturbation theory of matrices and verify that we agree from fundamentals that we have learned and can prove that this is a true statement. So that's, but for the purposes of, so I think when you're reading, if you're reading a paper, you could spend all day going into every single proof and trying to figure it out. So I think this is more important on the level of if you are putting your own proof in a paper. So right now I'm just going to assume that they're right, that this is true. But then if I was writing this proof in a paper, then I would say, like, let me look, be sure. So then let's talk about what this means. The eigenvalues of a matrix depend continuously on its parameters. So this is saying that if you change the values of the A matrix slightly, that the eigenvalues should, like, change slightly in some way. So, so then they start this epsilon delta arguments again. Did I get as far as telling you epsilon delta arguments before? Okay, that's good. So where this goes is, so then it says, this means that given any positive number epsilon, there exists a corresponding positive number delta, such that if the magnitude of the perturbation in each element of A is less than delta, the eigenvalues of the perturbed matrix A plus delta A will lie in open disks of radius epsilon, centered at the eigenvalues of A. So I'll also break this down. So if we look through this, it's saying that given epsilon, so you could say I give you an arbitrarily small epsilon or a larger epsilon or whatever. Then, so I give you some epsilon and it can be arbitrarily small. Then there's a delta such that if the magnitude of the perturbation, so then we would need to define magnitude of the perturbation, because the perturbation here is a delta A, which is a matrix. So then this would probably be something like a matrix norm, because we have to be able to reduce it. Here, delta is a scalar, so we have to be able to compare a scalar with a scalar. So that's why we say magnitude. If the magnitude of the perturbation in each element of A is less than delta, so given epsilon, so give me an epsilon, and then I will tell you that there is some amount where if the perturbation is in magnitude less than this amount, then the eigenvalues of this perturbed matrix, so A plus delta A, will be within epsilon of the eigenvalues of A in the sense of this open disk of radius epsilon. So that's also a very specific measure of in what sense they are close. So it'd be something like they're within a norm, like x minus, or the eigenvalue of the new matrix minus the eigenvalue of A or something is absolute value or something like that is less than or equal to epsilon, or it would be some type of metric that this is representing. So then the idea being like, oh, okay, so I could get, I can find a small enough perturbation for any small amount that I want the eigenvalues to change. And then, so what this means then for the linear system was that, so if the eigenvalues have positive or negative real parts, then they're not on the imaginary axis. So there should be some small range around them where it's not yet touching like the imaginary axis, for example. Because essentially you're in an open set. So like if you imagine, say your eigenvalue is even here, but you can always find a very infinitesimally small region around this because you're not on this line. So you should always be able to get infinitely closer to this line before you hit that line. So there should always be like here I am, and I'm looking for, you say like, okay, I want the eigenvalue to be like within this region epsilon. So I want my eigenvalue to my eigenvalues of my perturbed matrix to be within, here's the lambda of A, and so I want the eigenvalues of A plus delta A to be within like some small amount epsilon. First let me ask, is this okay?
Yeah, but even for the eigenvalues positive or negative with real parts, they can't be complex.
Oh, they could be complex. They're not on the axis.
Oh, okay.
Yeah. Mm-hmm. They can be complex though. But then the point being that if you have a positive or negative real part, you're somewhere off the axis. Okay. Mm-hmm. And then so that means that you should always be able to get infinitesimally closer to this axis because you're not actually on it. So there should always be like essentially like a limiting, like taking the limit, like I could take this small step or even smaller. So there should always be some small amount that you could go. So then if I made epsilon, like if I said, well, that's the epsilon that I'm talking about. Like that's small. Like, can you find some small amount that you could be different? And then if you can find a small amount, then I can say that, well, I could find an even smaller perturbation. So if I only have this far, that I could change the eigenvalues before it can approach the axis, for example. So the eigenvalue of A is some number. Say it's lambda 1. Then lambda 1, say it's like, then I'm like, oh, okay, for lambda 1 to remain, say it's negative. For lambda 1 to remain negative, maybe it's really, really close to the imaginary axis. Like real part 10 to the negative 10 or something. But if I added, I could say like, oh, okay, well, if I say, well, I want that eigenvalue to be within 10 to the negative 12 of the current eigenvalue 10 to the negative 10. So then epsilon, so then I can say like, okay, well, given this, if you tell me how close you want me to the original eigenvalue, so tell me you want me within epsilon of the original eigenvalue, I can find you some amount that the elements of A can be perturbed so that you get within that distance. Mm-hmm. So then that means that if I was to have an eigenvalue with a positive real part or a negative real part, because I haven't hit the axis, there's some amount that I still have leeway before I go to the axis. So there is definitely some amount that I could perturb A and still get a positive or negative real part of my eigenvalue, because I wouldn't have hit the axis yet. And this tells me that I will be able to perturb the elements by some small amount and still keep the eigenvalues of the perturbed one within a small amount. Does this make sense? Okay, cool. So if your eigenvalues have positive or negative real parts, then if your perturbations are sufficiently small in this sense, like that they're sufficiently small in this sense, which also depends on how close you are to the axis and stuff, then if they're sufficiently small, they stay positive or negative real parts with a sufficiently small perturbation. Oh, this is, I guess, if they have. So then, eigenvalues, I guess, if they're distinct. Distinct eigenvalues with positive or negative real parts. Then, so if the eigenvalues, though, are on this axis, then, so that would mean there's some zero real part. Then you can see how by trying to apply this theorem, you would say like, oh, okay, well, if you tell me that I want the eigenvalue to be within epsilon of the original eigenvalue, that even if you do that, like it could be in the negative side, it could be in the positive side, like it completely changed the, it made a significant change in the eigenvalue. So if all those phase portraits were based on eigenvalues, and whether or not they were zero or positive or negative, it's clear that this one is a little bit like just from saying like, oh, okay, my eigenvalue is on the imaginary axis. And then you say, well, say I perturb it. And then you say like, okay, apply this theorem. And then you say, well, I can't really tell what it's doing then. Because I don't know, this just tells me it's going to be within epsilon of the original one. But within epsilon means it could become positive real part. It could become negative real part. I don't really know what it did. So then that's partly why then there's this uncertainty if you have these. So I guess what that indicates is it starts hinting at the idea, okay, so I can prove what I've proved, or not even proved. What I have realized does not hold is I realize that from this theorem alone, I cannot tell what happens if I perturb the eigenvalues, or sorry, if I perturb the matrix A. So if I have an original system, x dot equals ax, turns out my original system has a slightly wrong matrix compared to my real dynamics. My real dynamics are A plus delta MA times X. And then you say, will the behavior, if you have a zero eigenvalue for A, you say, will the behavior, if the actual matrix was A plus delta A, be similar or not similar? And then you say, based on this theorem, I don't really know. Like, it seems like it could have got a positive real part and changed. It seems like it could have got a negative part and changed. I don't really know.
We cannot predict the stability of the system if the eigenvalues of the A matrix is zero.
I guess what this is saying is, from this theorem, you cannot conclude. Whether or not there are other theorems, I couldn't say. So this also gets to something called necessary versus sufficient. So conditions, if they're necessary and sufficient, what that means is, like, the conditions go both ways. So it'd be like, if this, then this. If the second thing, then the first thing. That would be necessary and sufficient if both of those hold. Here, though, we didn't say, so I guess this is, but here we haven't actually proved the reverse. Like, so here I just said, based on this theorem, if I apply this theorem and I read this, what this is telling me is that if I had a positive, like, if I had some amount that I want my eigenvalues to be within compared to the original, then I can find a perturbation A that can get my eigenvalues within that amount. But here I say, well, now I'm extending that and saying, like, okay, great. So say that I want my eigenvalues to be within epsilon for a case that they were originally 0, or one of them was 0, and then there's something. And then I say, hey, I'm wondering, will the behavior, like the stability and the phase portraits, will that kind of structural behavior change as a result of this perturbation? And then I say, well, let me see. I'm not really sure. Let me look and see what theorems I know right now. And I take this one, and I say, what does this theorem tell me will happen? This one tells me that if I want it to be within epsilon, so I want to be only slightly perturbed eigenvalues, I can find a perturbation in the matrix to keep me within that amount. And then I say, that's great. So it seems like I should be able to, I can definitely find a perturbation that will keep my eigenvalues not very different. And then I say, so if my eigenvalue is originally 0, what does that mean for me? And I say, oh shoot, if eigenvalue is 0 and I only perturb it a little bit, but then it could become anything, like positive, negative, I don't know. So I say, based on this information, I cannot provide you an answer to your question. Does that make sense? But I'm not able to say, I'm going to have to tell you there is no answer to your question. I say, based on this, I cannot provide you one. Whether or not there is one, there may be. This didn't say there's not an answer. All this said was the straight-up statement I made. Is that clear? Okay. That's something we have to be really careful about in proofs, that we never say more than we have demonstrated mathematically. So then it also turns out, so when A has multiple, so non-distinct, so non-zero real eigenvalues, they're not distinct, but they're like positive or negative. It says that in the book that infinitesimally small perturbations could result in a pair of complex eigenvalues. That's really interesting, and I'm not 100% sure that I see that, but it says that that could also kind of change the portrait behavior. So what I guess the conclusion that gets made then is, like, from just reading this and trying to say what's important for today. It sounds like they somehow realized that somehow in the proof of somehow they realized that if these were not distinct, other things could happen, and that was why they like made a point of saying this is if they're distinct. I don't actually fully understand this second part. So, but I guess that's related to the part about always think through all of your parts of your proof and make sure you've covered every condition. I don't really fully see that one. Okay, great. So then what this said and what this did not say. So then going back to the idea of what I was talking about last time. So last time I made it sound like that because of that perturbation theory, that was the reason that we could tell anything about the nonlinear systems. But when I read this last night, what I realized is that didn't actually say anything about a nonlinear system. That literally said a perturbation that is linear. Here are the results, and here's the theorem. And so that was why I realized I was non-rigorous and that I didn't really post the lectures from last time. So yeah. So I think it hints at stuff, but I also think then the book kind of what they did next. Then they went through and said like, here's the results from the nonlinear systems. You can see how that kind of made sense with what we just said for the linear one. So, if you were really doing a proof of this, you would have to literally prove this for the nonlinear system. Like, making the logical extension and saying, like, it sounds logical based on that is very hand-wavy and may or may not be true. There may be other conditions you're missing, like if you just do what I did the other day. Say, like, well, as you can see, if you had this perturbation, you know, it's kind of like a perturbation with a nonlinear system. Like, that's not true. Like, what does that even mean? A nonlinear system is kind of like a delta A. What the heck? So there must be an actual proof for what goes on with the nonlinear system. Like whatever, and whatever it is, it's something where in the book, let's also not go by the chart I wrote last time about stable nodes go to this or unstable nodes go to this. Because it seems like there's certain cases that do weird stuff. So I guess, like how we just said, there's this other case in the linear systems where if the two eigenvalues are the same, then this other thing happens. Like, I don't know even where that came from. So I think the best thing to do is to say, like, is to find the statement in the book that says the conclusion. So it says the following, and I think this will be the safe statements to take rather than the chart I made last time. It's a good thing we didn't post that chart. That also might be very confusing. So if the origin of the linearized state equation is a stable or respectively unstable node with distinct eigenvalues, then in a small neighborhood of the equilibrium point, the trajectories of the nonlinear state equation will behave like a stable, respectively unstable node, a stable of some type of node, respectively unstable. I'm not quite sure which type. If they mean those ones that, I'm going to assume that these types that they mean the types that are not just straight lines, though I'm not 100% sure. A stable, respectively unstable node. No, oh, focus. Focus. Or a saddle point. And then it gives something about like, and if the nonlinear system has certain other properties, then it doesn't even matter if they're distinct or whatever. So basically the outcome of this is, if you are needing to assess stability of a linear or of a nonlinear system at some point, then I would look back at this Khalil book, make sure that you know the conditions under which you can really use the linearization, because apparently there's some things about distinct eigenvalues and whether or not they're like stable nodes and what kind of node that is and or focus or obviously. So, but I would look back and then I would say, basically what this is telling me is there are many cases where the linearization is going to tell me good information about the local stability behavior for my system. But I guess what the conclusion was that, but if you're something else, the zero eigenvalues, then you're not really sure about the local behavior very easily. So that's great. Another point I wanted to make from what I was reading last night is that in mathematics, and I know I said this before, but I also thought this was helpful to realize again. We only have rigor really when we define what we mean in our topics in math. So I don't know if you remember, but on one of the first days we were talking about this, there was something about bifurcation. And I remember that I had written in my notes something about topological changes or something. And I said, I don't really know what that means. And then, so last night I was like skimming a few of the parts on the bifurcations. And it really helped because what they did is they like basically laid out what are we talking about. And I was like, oh, that's right. That's what we always need to do in math. Like every single thing that you do. And this is also a lot of like what we will do in our papers. But in everything you do, you have to make sure you've defined what you really mean. So there can't be any loose like concepts. So you know how when we write in our papers, here is this function. And we'll say like, this is an economics-based objective function. It's a metric. It's a function that describes the economic behavior of your system. We write it as a function. So we didn't just say, I'm going to optimize something about the profit. So then like, what does that mean? What are you actually doing? What we said is, I'm going to require someone makes a function. It can be a function of the states and the inputs. If they make a function, I'm going to say, try to make that represent your profit in some way. But what it is, mathematically, and for all intents and purposes in the papers, it is a function of the states and the inputs. So it's really important because like here's what they said about the bifurcations. They said the qualitative behavior, so like kind of the way it behaves from a look perspective, of a second order system, like what we just said, is determined by the pattern of its equilibrium points and periodic orbits, so that would be like the limit cycles, as well as by their stability properties. So it's talking about like kind of where are the equilibrium points, what are they, what's the order, do you have like stable, unstable, stable, like across, like if you were to have, say, you have a real line, you have 3 equilibria or something. They go like stable, unstable, stable, or like unstable, stable, unstable, or like how are they organized? And so things like this, what are your equilibria? Are there limit cycles? How are they ordered? Where are they located? What are their stability properties? And it said that people are interested in knowing like if there are certain things in the second order systems that are perturbed compared to an original, does that change the equilibrium points or the periodic orbits or their stability? And as they said, when it does those things, then we're going to call that bifurcation or whatever. So I'm like, oh, that's always helpful to realize like definitions are so important in math. It's like, what exactly are we talking about? And yeah, that will underlie everything.